Friends, welcome back to my YouTube channel. In this class, I am going to discuss about second law efficiency. Before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. You see, there are two performance measures. One for work producing device like heat engine. We use for heat engine we use a performance measure which is known as efficiency, which is denoted by eta. This is a performance measure of work producing device like heat engine. At the same time, for work consuming cyclic device like heat pump, refrigerator, we use another performance measure that is known as coefficient of performance. But the question is whether these performance measures are sufficient to give a clear picture. The answer is no, because sometimes these efficiencies can be misleading. In fact, these performance measures like efficiency and COP are measured in the light of first law of thermodynamics. That's why they are called first law performance measures, and this efficiency is called first law efficiency. So, for example, you see how first law efficiency or simply thermal efficiency, what we calculate always, can be misleading sometimes. So then we'll go to second law efficiency. So you see, first law efficiency, that there are two heat engines working. First, we'll study about engine A, which is working between a source temperature of 600 Kelvin and sink temperature of 300 Kelvin, and heat supplied to engine A is suppose 600 kilojoule, and it produces 180 kilojoule of net work. So what is the thermal efficiency of engine A? We know that efficiency is the ratio of net work output and heat supplied or heat input, W net A divided by Q1A, and this is nothing but 180 kilojoule divided by 600 kilojoule, because here net work output is 180 kilojoule and heat supplied to engine A is 600 kilojoule, and dividing this comes out as 0.3, and in terms of percentage it is 30%. Similarly, for engine B, you see source temperature is suppose 1000 Kelvin and sink temperature is 300 Kelvin, and for engine B the heat supplied is 1000 kilojoule and it produces net work output of 300 kilojoule. Then for efficiency will be net work output divided by heat supplied. This is also 300 by 1000, that is 0.3 or 30%. You see, both the engines A and engine B are of same thermal efficiency. So if one goes by only first law efficiencies, he would conclude that both the engines are performing equally well, but that is not reflective of true scenario, because what are the maximum efficiency that can be an engine have is what has not been taken into account here. So you know what is the efficiency of a reversible engine? If engine A operates in a reversible manner, that means you know that when an engine performs a cycle means it consists of series of processes. If all those processes are reversible, then its efficiency would be maximum according to Carnot theorem, and its efficiency, maximum efficiency will be, so efficiency of reversible heat engine that is, if the engine A operates in a reversible manner, its efficiency would be 1 minus sink temperature is 300 divided by 600. This would be nothing but 0.5 or 50%. In place of 50%, the actual engine A is performing with an efficiency of 30%. And as far as the reversible engine B, efficiency of reversible engine B, this is equal to 1 minus 300 divided by 1000. This is 0.7. So in place of 70%, the actual engine B, which is not reversible, is operating with an efficiency of 30%. So its potential is, it can achieve 70%. Under the given conditions, if engine B operates in a reversible manner, it can attain an efficiency of 70%, but it has achieved 30% only. On the other hand, engine A has the potential of achieving 50% efficiency, whereas it achieves only 30%. So obviously, if one would go by the potentials, one would definitely suggest that the engine B has performed poorly relative to engine A, because its potential is higher. Its potential is 70%, but it has performed only 30%. So there is enough room for improvement. And as far as engine A is concerned, its potential is it can achieve 50%, but it has achieved only 30%. Suppose, for example, if you take a real life example, there are two students. Suppose student 1 has potential of scoring 90% in an entrance exam, and student 2, second student, has potential of 80%, scoring 80% in an exam. And if student 1 has achieved 80% only, and second student has achieved 80% also, then we can say that second student has done better as compared to first student. You can conclude that both have done equally well, because the student 1 is having higher potential. He should have secured 90%. In place of that, he has scored only 80% due to some negligence or any other reason. So we can't say that both students are having equal performance. In fact, student 1 has performed poorly. So second, when we take the performance of reversible engines or reversible refrigerators or reversible heat pumps into account, that means we are calculating in the light of second law, because second law distinguishes between processes and second law affixes a quality index to energy. When we calculate first law efficiency, we do not affix any quality index to energy, any quality dimension. No quality dimension is given to energy, only quantity aspect we are concerned with. So second law efficiency can be defined as actual efficiency divided by maximum efficiency, that is the efficiency of a reversible heat engine. Similarly, second law efficiency for a work consuming device will be COP of actual work consuming device divided by COP of reversible device. So if you want to calculate second law efficiency of this particular example, second law efficiency of this engine A would be, actual efficiency of engine A is 30%, but its potential is 50%. That means the efficiency of a reversible engine A, that means if engine A works in a reversible manner, then its efficiency would be 50%. So second law efficiency of engine will be 0.3 divided by 0.5. So this is equal to 0.6. If you want to calculate second law efficiency of engine B, this would be actual efficiency 0.3 divided by reversible, the efficiency of reversible engine B is 70%. So 0.3 divided by 0.7. This would be 0.43. So obviously here the second law efficiency of engine A is higher than that of engine B. That means in terms of second law efficiency, engine A is performed better as compared to engine B. So you can't conclude that both the engines are having equal performance. So if you had gone by the first law efficiency only, you would have got a wrong conception that both are having equal performance. So second law efficiency is needed along with first law efficiency to get a clear picture of performance measures of various devices. So one question must be coming into your mind. So these are the formula which can be used for work producing or work consuming devices. And of course these devices are cyclic devices. So what about a simple device in which there is only processes occurring, not any cycle completed? That means any non-cyclic device. In that case, you can have a more general definition of second law efficiency, and that is actual work divided by reversible work. If it is a work producing device, and if it is a work consuming device, then the efficiency, second law efficiency would be reversible work consumed divided by actual work consumed by device. Just like a compressor. Compressor is not a cyclic device, but it's a work consuming device. So you know why this change in numerator and denominator is taking place? Because you see, in case of work consuming device, work consumed is least when the process is reversible. And in case of work producing device, work produced is highest when the process is reversible. So that's why, and efficiency is always going to be between 0 and 1. It can never be greater than 1. So obviously a larger quantity must be in the denominator. So another definition can be in terms of exergy, because you see there are some devices like heat exchanger where neither they are work producing device nor work consuming device. So how to calculate second law efficiency for them? So second law efficiency in that case will be exergy recovered divided by exergy expended. Exergy is nothing but work potential. What is the potential, maximum potential of useful work that can be extracted from a source? So what is the maximum useful work that can be extracted from certain heat input or certain form of work or enthalpy? That represents your exergy. So second law efficiency is what is the exergy recovered and divided by exergy expended. You know, whenever someone talks about the energy conservation nowadays, means we have to conserve energy in terms of quality, because quantity wise energy is always conserved according to first law. You have nothing to do with this. So whenever you talk about conservation of energy, that means you have to minimize the destruction of exergy, because destruction of exergy is bound to happen. But what we can do is we can minimize the destruction of exergy, so that second law efficiency would assume a higher value. More the exergy recovered, more would be the second law efficiency for a given exergy input or exergy expended. Take for example, and this is the most general definition. You see, this is the most general definition. This can be applied for any device, be it heat exchanger. A heat exchanger में क्या होता है? Neither work is produced nor work is consumed. But if when two fluids are mixed with each other, exergy is lost by a hot fluid and exergy is gained by the cold fluid. In that case, we will calculate these two things: exergy recovered and exergy expended. Exergy is expended by the hot fluid and exergy is gained by the cold fluid. And this formula or this concept can also be, this formula, in fact, this is the most general formula, and this can be, before this I have already explained two more formula. This is the another formula, and first, this is the first formula that I have explained, that is second law efficiency is this one. So there are three formula, and this is the most general, and this can also be applied for any heat engine. So that's all. Thanks for watching.